Let us do some problems in subgroups. The first problem we are going to attempt today is find the order of cos 2 pi by 3 plus I sine 2 pi by 3 in U6. U6 is the group of sixth roots of unity. That means there will be there will be 6 points here. This will be here, probably somewhere here. This is 1 point. This will be actually 60 degrees. So this is another one, this one, and you have another point here and then another point here. This is, we can call it as zeta, and that is equal to cos 2 pi by 6 plus I sine 2 pi by 6. So there are 1, 2, 3, 4, 5 and 6. This is actually set as square. This is going to be set as cube, set at the power of 4, set at the power of 5 and set at the power of 6. This will be probably a little bit, okay, that's fine. So if zeta is equal to cos 2 pi by 6 plus I sine 2 pi by 6, then U6 is equal to the cyclic group generated by zeta. And the elements of this will be zeta square, the cube, zeta 4, zeta 5, and zeta 6 will be our identity. So let's call it as. So this is equal to the identity map, identity element. So here, this actually is zeta square. What is zeta square? If zeta is equal to this, zeta square will be cos 2 pi by 6 times 2 plus I sine 2 pi by 6 times 2. And that is equal to cos 2 pi by 3 plus I sine 2 pi by 3. So we are asked to find out the order of, asked to find the order of zeta square. So the order of what is the zeta square means? The order of the cyclic group generated by zeta square, or zeta square to the power of n is equal to e, and this, the lowest element, the lowest integer n is the order of zeta square. We know that zeta to the power of 6 equal to e. So the order of zeta square is 3, because zeta square cube is equal to Our next problem is this. Let G be an abelian group. And H and K are subgroups of G. Then HK is equal to HK. H belongs to H and K belongs to K is a subgroup of G. It's important that it's an abelian group. So how do you prove that a subset is a subgroup? Three conditions. HK is closed. Second condition, E belongs to HK. And the third condition is for A belongs to HK, A inverse belongs to HK. If these three conditions are satisfied, then HK is a subgroup. So in order to prove that HK is closed, take two elements and find the product and see that it is in HK. So let A comma B belongs to HK, and that implies A is equal to H1 K1 and B is equal to H2 K2 for some H1 H2 belongs to H and K1 K2 belongs to K. So that means AB is equal to H1 K1 H2 K2, and that is equal to H1 H2 K1 K2 because K1 H2 is equal to H2 K1 because G is abelian. G is abelian. And that is equal to HK for H is equal to H1 H2 and K is equal to K1 K2. And this belongs to H and this belongs to K. And that means it belongs to HK. So this is done. This is very simple. E belongs to H and E belongs to K because they are subgroups. That implies E times E is equal to E belongs to HK. So that is easy. Here A belongs to HK implies A is equal to HK for some H in H and K in K. So A inverse is equal to HK inverse, and that is by definition it is K inverse times H inverse, and that is equal to H inverse K inverse because G is abelian, and that implies this belongs to HK. So this is also, that means HK is a subgroup of G. Proof is very simple, but make sure that you follow the only the properties of a group. Our next problem is let G be a group and H is a subset of G. Then G is, sorry, then H is a subgroup of G if and only if for all A comma B in H, AB inverse belongs to H. So the first part is very simple. That is, if H is a subgroup, then A comma B belongs to H implies B inverse belongs to H. That implies AB inverse belongs to H. So that is very simple. The second part is, let A comma B belongs to H and AB inverse belongs to H. Then we need to prove that H is a subgroup. So we are going to prove in a slightly different order. So first one we are going to prove is E belongs to H. Second, we want to prove that for A belongs to H, A inverse belongs to H. Third, we are going to prove H is closed. So if these three conditions are satisfied, H is a subgroup. This is very simple because A comma B belongs to H and let B equal to A, and that implies A times A inverse belongs to H implies E belongs to H. So that is done. Here AB inverse belongs to H, and that implies if A is equal to E and B is equal to A implies E times A inverse belongs to H, and that implies A inverse belongs to H. So that is also done. Here the third one, A comma B belongs to H. That implies B inverse belongs to H because of the second property. Not because H is a subgroup. We are yet to prove that H is a subgroup. B belongs to, for every B belongs to H, B inverse belongs to H because of 2. And that implies A times B inverse belongs to H, because this B inverse belongs to H, A belongs to H, and from the assumption B, AB inverse belongs to H, and that implies AB belongs to H. So that implies H is a subgroup of H. Our next problem is, if G is a finite cyclic group with one generator, then G has at most 2 elements. So if G has only one element, then G has only one generator. So if G has only one element, then it's got only one generator. Suppose G has n elements and A is the generator. There's only one generator. Then G is equal to E A dash dash A to the power of n minus 1. If A is a generator, so is A inverse, because A to the power of I is equal to A to the power of minus 1 minus I. Or you can say n minus I. Or you can say A to the power of minus 1 to the power of n minus I. Both are same. So A and A inverse are generators of G, and A inverse is equal to n minus A inverse is equal to A to the power of n minus 1. This is because A times A to the power of n minus 1 is equal to A to the power of n is equal to E. So the inverse of A is A to the power of n minus 1. And that implies, see, A and A inverse are the generators, and there is only one generator. That means A is equal to A to the power of n minus 1. And that implies n minus 1 is equal to 1, implies n is equal to 2. So the maximum number is 2. If it is not, if G has got more than one element, it can have two elements. So that means G has at most two elements if it has only one generator. Our next problem is this. If G is a group that does not have any proper subgroups, then G is cyclic. So proper subgroup means we are excluding the G itself. So there is no proper subgroups for G. The only other subgroup is the trivial subgroup. So let A different from E belongs to G. Then A is the subgroup, the subset generated by A is a subgroup of G. And because G does not have any proper subgroups, G must be A, and that implies G is cyclic. Our next problem is find the order of 25 in C30. What is C30? Is equal to 0, 1 dash dash 29. So we need to find out the number of elements of the subgroup generated by 25. So this actually, what we need to see is, we need to find out 25 plus 25 plus dash 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 25 should be a multiple of 30, because this has to be E, and that is actually 0. If this has to be 0, then this sum has to be a multiple of 30, because it's addition and a modulo 30. So how do you find this? You find the GCD of 25 and 30, and that is actually 5. Then so that means 30 times 5 is equal to 25 times something. So P is equal to 30 times 5 by 25. And that is equal to 30 by 5 is equal to 6. Meaning if you add 25 6 times, you will get a multiple of 30. So this will be 6. Basically the method is find GCD of 30 and 25. Then 30 divided by the GCD of 30 and 25, and that is equal to 30 by, this is actually 5, and that is equal to 6. Our next problem is, let ZRS equal to MR plus NS, M comma N belongs to C, then ZRS is a subgroup of G. Again, we follow the same rules. ZRS is closed. Then E belongs to ZRS. Then for every A belongs to ZRS, A inverse belongs to ZRS. So here A comma B belong to ZRS implies A is equal to MR plus NS, N1 R1 plus N1 S1 S, and B is equal to M2R plus N2S. So A plus B is equal to M1R plus N1S plus M2R plus N2S, and that is equal, that implies that is equal to M1 plus M2 R plus N1 plus N2S, and that belongs to Z of RS, implies A plus B belongs to ZRS. This is clear because E belongs to ZR. E is equal to E times E plus E times, okay, this is actually, yeah, this actually is E 0 times R plus 0 times S. That means 0 belongs to ZRS. So this is also done. And here this one will be A is equal to MR plus NS implies M minus MR minus NS belongs to ZR. That implies A inverse belongs to ZRS. So this is also done. So ZRS is a subgroup of, we'll do our last problem in this section. Let G be a group. Then if for A comma B belongs to G, the order of AB is finite, then the order of BA is same as AB. See, we are not saying that A is an abelian group. It's just a group. Okay. So, if the order of AB is finite, then it is the same as the order of BA. So, let the order of AB is n, and that implies AB to the power of n is equal to E. Now, BA to the power of n plus 1 is equal to BA n times, n plus 1 times, right? So if you take this group, that means B times AB times AB times AB n times A, and that is equal to BAB to the power of n A, and that is equal to BEA, because the order of AB is n. So that means BA, this is actually A times B is A. So this is BA. So this means that BA to the power of n plus 1 is equal to BA implies BA to the power of n is equal to E, and that implies the order of BA is less than or equal to n. If BA, the order of BA is less than n, then with the same argument, we arrive at the order of AB is less than n. But we assume that the order of AB is equal to n, and that implies the order of BA is equal to